Okay, so good morning, everyone. As a director of this ASPIRE program sponsored by JST, I'd like to welcome you all, and especially those who came across the troubled continent. And I don't know how you could get here, but anyway, we're on both sides of the continent, which in the middle there is some trouble. And so this kind of activity is getting harder and harder to have. But because of that, we have more reason to have this type of joint meeting. Now, ASPIRE was started 3 years ago, and it was intended to sort of promote international exchange of young talents, especially to promote young early researcher or early career researchers to go abroad and spend prolonged time in other institutions and have good friends and be involved in the activity there and be a significant part of their research. So I hope you all understand this motivation of activity and have good time and have put some effort into this to get this activity research end. Now, we know that through the COVID-19, we learned that it's actually very difficult to interact closely through web, through internet. And personally, the biggest difficulty for me was I cannot whisper the next guy, to the guy next to me, because you are not supposed to be heard by everyone. So, and this kind of information, something like, oh, do you understand this guy? And no, I don't either. This kind of information may be actually important to have what the other guy is actually thinking, other than just say something in official open scene. So, I wish you have good chance to exchange deeply and understand each other, and try to utilize or exploit this opportunity to the last drop. So with that, well, thank you very much. I wish you a good meeting.
All right, so good morning, everybody. So welcome to RIKEN AIP. So my name is Masashi Sugiyama. I'm director of the center here. So welcome from the UK. So it was a long trip, and I'm quite happy to have you here. So spring came to Japan, so please enjoy your stay in Japan. So let me briefly introduce our center, RIKEN Center for Advanced Intelligence Project. So before starting, let me talk about RIKEN itself. So RIKEN is a relatively old institute, started in 1917 as a private foundation, actually. But compared with UK universities, it's much younger, but still it has already more than 110 years. 110 now. Yeah. So then actually RIKEN became quite big. So it was called RIKEN Concern, and in 1939, so RIKEN had 63 companies and 121 plants. So it was a big entity. It was quite successful, and I heard it was quite rich at that moment. But unfortunately, after the World War II, RIKEN was regarded as a kind of dangerous entity, and it was broken up. But then in 1948, RIKEN restarted as Scientific Research Institute, and then it became a public organization. And now we are called National Research and Development Institute, and we are under the Ministry of Education, Culture, Sports Science, and Technology. Then now RIKEN has actually 4 major domains. So they are respectively physical science, sustainability science, life science, and mathematical, computational, and information science. And we belong to the last domain, and our Center for Advanced Intelligence Project is included here. Then the RIKEN AIP. So RIKEN founded our center in 2016, 10 years ago, as a center for the next AIP project. It was actually a 10-year project started in 2016, and it was just completed last month. So we finished the 10-year project. Then from this month, so we became kind of version 2 AIP. And this AIP2 is a kind of regular center in RIKEN. So we will conduct still like basic research in AI and machine learning. So currently we have about 130-40 employed researchers, and more than 40% are international, and about 1/4 are female researchers. So we are quite diverse. And in addition, we have more than 300 visiting researchers from different universities and industry. And also we have more than 100 domestic students as part-time researchers. They are mostly PhD students. Then in addition, so we accept a lot of interns. So during the COVID time, for 3 years, we couldn't accept any interns. But otherwise, so we accept maybe regularly about 30 students per year. So now we accepted more than 220 students. They are extremely active. And so the good thing is, so interns came to RIKEN and we worked together. Then, okay, they did some work and go back. Then they finished their PhD in their own countries. Then, okay, some of them decided to come back to RIKEN again as a postdoc. Then, so some of them are working already here. And this is a very nice kind of ecosystem for us. Then in addition to our Tokyo office, so our offices are basically distributed because we have team directors from different universities, like from Sendai, Kanagawa, Nagoya, Osaka, Kyoto, Fukuoka. So it's distributed. Then now in RIKEN AIP, so we have 3 research groups. So they are named Mathematical Intelligence, Domain Intelligence, Physical Intelligence. So the Domain Intelligence group so develop AI technology specialized for domains such as science and industry. So basically their target is AI for science. So now it is quite important. Then the second group, Physical Intelligence. So they develop AI technology adapted to diverse data from the physical world. So this is basically AI for like a physical world and robotics. So physical AI is nowadays one of the most important challenges for the community. Then the last part, mathematical intelligence, so tries to like elucidate the fundamental principles of the state-of-the-art AI technologies and try to create new concepts for high reliability AI. So basic research is always a kind of driving force for us. So we need to really spend energy to develop something new here. So these 3 groups are like working, of course, independently and at the same time collaboratively like this. So we hope to develop something really impactful for the future. Then so we have 3 groups and many teams in each group. And I also have a team here, and Ishida is a member of my team here at RIKEN, but Ishida is also an associate professor at the University of Tokyo. And Wenkai was an intern long time ago, so 2019 you said. So great, so he's back now and having the project together. So that's really an amazing thing for me. Okay, anyway, so we have a lot of also international collaboration partners, and many actually people are visiting RIKEN and giving talks and having collaboration. And this is, of course, one of the most important opportunities for us to talk about safeguarding, statistical safeguarding. So that should be one of the most important topics for the future. So I'm, anyway, quite happy to have you here, and let's enjoy the workshop today. Thank you very much.
Okay, right. So this talk is actually very related with Takashi's talk. I think this is a very well organization of this workshop. As you will see later, it's connected in 2 ways. Takashi talked about the Bayes error, and I'm going to talk about the minimax risk. It's deeply connected, and I'm also going to use. Basically, I'm going to talk about the privacy, and I'm going to talk about a specific type of privacy called differential privacy. That's exactly some from the audience talking about the flip a coin to get the randomized response. So you will see. Okay, so differential privacy, right? Differential privacy, I'm going to introduce it formally later, but I just want to first motivate this is not just mathematicians, statisticians' toys. This is really used in the real life. I have 4 examples here. The top left panel, this is just a screenshot from New York Times. It's not an eye test. I'm not asking you to read the small fonts here. Basically, the caption of this screenshot is to say, if you read the 2020 US Census results, they actually say under this band of Chicago River, there are 14 residents, okay? It's fictional, right? And this is exactly from the audience that is a benign noise added in order to protect the individual's privacy. And the privacy type they use is a specific thing called the central differential privacy. Okay, I'm going to give formal definition later, but at a high level, you can think is there exists a central data curator. In this sense, is the US Census Bureau. They have access to all the raw data, and they manipulate it, release some results in order to protect the privacy. Okay. Similar example is also used in the United Nations, and that is the top right panel. This is from counter-trafficking data collection. So this data set includes 18,000 real victims and 20,000 real perpetrators. Of course, all this is a highly sensitive information, but they publish some statistics you can study, and all these statistics they use is actually subject to the central differential privacy. Okay, so in these cases, you think, okay, we allow someone to have access to our raw data, United Nations, US Census Bureau, but sometimes there's information I don't allow anyone else except myself to have it. So that requires a stronger notion of differential privacy, which is a local differential privacy. Only you have the right to own your raw data. So that is actually implementing a lot of tech companies these days. For instance, Apple. Well, they say Apple do not see your data. So when they collect the data from your iPhone, from your watch, or whatever thing, they only collect a perturbed version. So only you have access to your own raw data. Okay, there's an even stronger notion called the user level. If time permits, I will give a formal definition later, but this user level thing, this is used in the Google About Gemma. It's a differentially private LLM. Anyway, so for now, I just want to motivate you. The concept I'm going to introduce formally, this differential privacy, is not just for mathematicians to do some equations. It's really used in the daily life. Okay, so that is one part of the talk I want to talk about, is differential privacy. Another thing is also from the title, is federated. By federated, what I mean is these days, data are very decentralized. This is a cliched example for the decentralized data. So, for instance, the medical records, I probably have to trust my own doctor in the hospital I go to, but I probably don't really want doctors from other nations or from other regions to have access to my raw data. But in order to understand what's happening or do some clinical trial, you have to aggregate all the information from all different institutions you can get. So data itself is decentralized, but the trust is not uniformly across the whole world. Okay, so the data decentralized, and then we probably want to use some privacy methods to learn things jointly. That is the federated learning we're talking about. Okay, so federated learning itself is not new. We have the federated EHR, it's electronic health records, or there's the Melody thing. Melody is a consortium of more than 10 pharmaceutical companies. They want to jointly build some AI system, but they hold their data privately within their own company. Okay, so hopefully I've motivated you enough that privacy is important, and the differential privacy is also already very well embedded in our daily life, and also a lot of important sensitive data, they are decentralized. So what I'm going to do for the rest of this talk is just to say how we can do this in a rigorous private way. Okay. Right. Okay, so for the rest of my talk, I prepared this talk you may feel like it's almost like a job talk. I will probably go into one of the paper in slightly more detail, but I also want to give you an overview of my research in the differential privacy. And well, I'm happy to chat later or offline or in the future to see if there are some collaboration opportunities. Okay, so for the rest of my talk, I'm going to give you definitions, some formal definitions, rather than just hand-waving motivation. And I'm going to give you a selected review of the federated differential privacy, and I will finish with some open problems or some ongoing things I've been thinking of. Okay, first thing first, differential privacy. Okay. Enough about motivation. Let's come to some maths. What is a privacy mechanism? So when we say a privacy mechanism, it is a conditional distribution, condition on your raw data, and you output your perturbed version. Okay, so when we say a privacy mechanism, it's a conditional distribution, conditional on raw data. And in order to satisfy the differential privacy, we need to add some conditions for this conditional distribution. And think about what we mean by privacy. By privacy is, I don't really want you to know about the real me. Say, Wenkai's data and my data put on the table. If we care about our privacy, we don't really want you to be able to tell for certain which data is whose. So that is the indistinguishability. Okay, then put in maths, the indistinguishability is to say these two a pair of conditional distributions, they are indistinguishable in the sense of one, okay? So delta is some privacy leakage. Delta can be very small. It's for, most of the time it's for practical use when you come to some dealing with some complicated distributions. So delta is something extremely small, and if you ignore delta for now, basically it's the ratio of these two distributions is upper bounded by e to the epsilon. Epsilon is something between 0 and 1. Epsilon is something larger than 0, and the smaller epsilon is, okay, if epsilon equals 0, sorry, it's just 2 prime. If 1 epsilon equals 0, e to the epsilon is 1, which means no matter how different your x and x prime are, these two conditional distributions, they are identical, right? So the privacy is perfectly preserved in this sense, but you learn nothing from data. And a large epsilon, well, the trade-off, you leak your privacy, but you can know your data better. Okay, the central differential privacy, as I said, well, in the US Census, the Census Bureau, they have access to all the raw data. So the input is all x and x prime, and this x and x prime, they are the sample size n, and by a pair of distributions here is to say x and x prime, they differ by at most 1. If this is a little bit too arbitrary, let's have one interpretation of this definition. The interpretation is to say, okay, I have x1 up to xn, they come ID from a distribution P, and I know P, I know the distribution, I know their ID, I even know your privacy mechanism, I know what your conditional distribution is, and I can fake users, I can attack your system, I fake n minus 1 users, I know what x2 up to xn is, okay? I know all this, I just want to know you. You are x1, okay? So as long as this z is coming from this epsilon delta central DP mechanism, I will not be able to tell your data for certain. What does that mean? That means if you are doing a statistical test and h0 is x1 equals 1, alternatively, let's say x1 prime, the power of this test is upper bounded. So you cannot tell apart with larger probability, okay? So that is what this definition is talking about. probably need to hurry up a bit. If this is a bit still a bit too abstract, I can give you a concrete example. So if I want to know the average salary of the professors in RIKEN, and what I can do is I can probably go to the HR, because HR has all the raw information. I can go for HR, I can say, okay, take the average and add some Laplace noise. What I'm not going to show now is, I'm not going to prove to you now. I just want you to trust me. This definition, this estimator here satisfies epsilon 0 dp, which I've already defined, and also this is minimax optimal. This is the best you can achieve in terms of in the minimax sense. Okay, so what I want you to pay attention to is, for the central dp in this sense, the variance of total added noise is over order 1 of n squared epsilon squared, 1 over sample size squared budget squared. Okay, right. If it's not about the salaries, let's say I want to know something more sensitive, more personal about an average professor in RIKEN. I want to say how many chocolate bars you consume. HR wouldn't know that. And if I want to do that, only you have the information for your data. Then what I can do is I can use the local differential privacy. Okay, and I can go for every one of you, tell you to perturb your data by adding a scaled Laplace noise and average that. Again, I'm not going to prove this is satisfy epsilon 0 local differential privacy. I'm not going to prove this is a minimax optimal, but just trust me. Okay, so anyway, in this sense, the variance of total added noise is of order 1 over n epsilon squared. If you compare this to the upper one is central, there is some central data curator have access to all the raw data. So, and the good thing is, the accuracy loss is just of this order. It's 1 over n squared epsilon squared. But if you want stronger privacy, then you pay a larger cost. And it's 1 over sample size budget squared. Okay, so this is some example. And I said we're going to talk about the decentralized data. So this is basically a simplified plot of this cliched hospital example. And what we have is, let's say we have as hospitals, as users, as servers. I'm not going to differentiate the terminology here. And each server holds NS copies of data. And the federated differential privacy or federated learning under differential privacy, the idea is each server, you output some private release subject to some form of differential privacy. And you have a central server to collect all the private information to learn the thing jointly. So this is basically the so-called federated learning and the differential privacy. Okay, and there are a whole loads of different, so if you see my orange text here, I said some form of differential privacy. There are loads of different forms of differential privacy, way beyond the central and the local I just introduced to you. So, and then in this federated learning setting, there are loads of different terminology too. I'm not going to detail for all of this, but I just want to focus on probably the last one here is the federated DP. So the federated DP, in the sense, back to this simple plot, is basically to say within each server, it's central DP. But if you stand on the server level, you treat each server as a user. At the server level, it's local DP. So that is the so-called federated DP, okay? So I trust my doctor, and they release something. They are the central data curator. They have access to all the patients in this hospital. So that's it's a central DP within one hospital. But I don't want to share any raw information with other doctors in other hospitals. So only private information can be transmitted across servers. So that is the so-called federated DP. And okay, I'm just being aware of the time. Okay, so that's just a very quick overview of my work. So I've been doing things on online learning, like multi-arm-banded problem with dynamic pricing, and you can do it in a differentially private way. And there are different data types. Yeah, basically everything can be privatized. And there are different statistical tasks, estimation testing, or even inference. So you can also do all these things in a private way. And there are also additional challenges. So this is something I'm probably, if I have time, or I can talk offline. So in addition to you want to learn data privately, there are some other challenges coming in. So for instance, you want to also learn things in a fair way, so you also want to do it subject to some fairness constraints, and you also want to do some contamination, you want to learn it in private, a robust way, and of course, as you can imagine here, what I'm going to talk for this talk is I'm just going to talk about things. It's homogeneous. It's ID data for all different servers. So you can see it can be different distribution in different server, can be different sample size, different privacy budgets, or different data type. Anyway, so all these sort of things. There are many open problems in this area. Okay, right. So I think I have 10 more minutes. Yeah, okay, I said there are at least 2 connections with Takashi's talk, and this is the second connection. So a flavor of my work is I want to understand the so-called, we call cost of privacy. It's a fancy way to say things, but basically this is to say we want to understand the minimax rate. We use minimax rate as a way to quantify the fundamental cost of fundamental hardness of a problem. And if you have a minimax rate for the private problem and a minimax rate for the non-private problem, you will see what is the cost of privacy. Okay, so I'm not going to bombard you with the definition here. Basically, that's the minimax rate. Okay, then I told you we want to quantify the cost of privacy. Therefore, we use the minimax tool. If you still feel not fully convinced, I'm just going to show you a very simple example. So I had this univariate mean estimation problem to introduce the privacy. Now let's look at this problem again. So this is the simplest possible problem. We just want to estimate the univariate mean, and it's measured in squared loss. And in this federated setting, we have S hospitals. Each hospital has n patients. Okay, so I have different rows here. The first one is no privacy, and it's a corresponding minimax rate. And then this is all different. I'm not going to detail, but as you can see, there are way more rows you can write here. There are many different types of privacy constraints. Okay, and with all these different additional ones, as you can see, of course, they are more difficult than without the privacy constraints. So of course, the no privacy rates will carry on. But for different privacy constraints, they have very different minimax rates. Okay, so this is something very useful. I didn't introduce the user level privacy in detail, but user level privacy is the one used in the Google Vault Gemma thing. As you can see, depending on how large your n is, this rate can be polynomial or exponential. So think about that. So US Census, right, or whatever organization, before they started to collect the data, before they started to analyze data, they need to set the privacy notions first. And there are loads of different notions to use. Even when you decided to use one notion, there's also a whole range of budgets you can use. But how can you decide it beforehand? There are many ways. We're not saying this is the only way, but this will give you an idea what is the fundamental cost of implementing a certain notion of privacy with a certain budget. So that is a key motivation for us to understand this cost of privacy, the minimax rate. Okay, so, well, I have 7 minutes left. This is a concrete problem. Maybe I will just briefly talk about it. Okay, so think about each green box is a hospital, okay? Each green box is a hospital. We have S hospitals, and each hospital has N or NS patients. And each patient is wearing an Apple Watch or some wearable devices to monitor some to monitor some index of you, okay? So you can think each curve here is one patient, and each dot here is one reading, okay? And then there's a, it's just so bright. There are NS patients within a hospital, and there are S hospitals together. So for this one, actually, if you stand on the hospital level, this is local DP. Only private information can be transmitted. If you zoom into a hospital, the doctor have access to all the raw data, so it's central DP. And if you zoom in each person's daily recording, I'm sorry I didn't introduce that notation carefully, but that's an even stronger notion. It's called the user level. Maybe a high-level way to understand the user level thing is, for instance, I have 100 recordings of my heart rate per day, okay? But to say what you want to understand is my average resting status heart rate. So what you want to estimate it is actually a univariate thing, but your data is a high-dimensional thing. A user level means you need to perturb a high-dimensional thing, but your inference task is just a univariate thing, okay? Anyway, so this is basically a mixture. And this is our data type, and this is our privacy constraints, so it's a mixture of everything. And the task we are doing is, okay, is you want to estimate, we are doing a functional data analysis, which means we want to have the mean curve. We want to understand this mean curve thing. And this is very standard here. So your readings will be X, Y. X, you can think, is the time of your recording, and Y is the corresponding recording of the recording value. And the model is Y equals mu plus U plus C. So the mu is a deterministic function we want to estimate. U is a random function, so it's the functional noise. And the C is a univariate random variable, it's a measurement error. This is all standard functional data. So if you are familiar with it, I'm sorry. If you're not familiar with it, I didn't explain it well. I'm sorry for that. But anyway, under some assumptions, that's the thing we want to say. Under the some assumptions, this is the results we have. So if you want to estimate the L2 norm, square the L2 norm of this function, and the minimax rate under this complicated privacy structure is as follows. As you can see, we can understand this rate from a few different aspects. So the first thing is, these two terms with epsilon there, those are the privacy terms. Those are the epsilon is the privacy budget. So this is actually the cost of privacy, and this is the fundamental cost of this problem without privacy. And we can compare the private rate and the non-private rate. So for instance, we can see, well, if we compare the first term and the third term here, there's an extra epsilon square here, and this is n square. If you remember what I said previously, the central differential privacy, the rate is 1 over sample size squared budget square. And for the local, is 1 over sample size budget square. So here, as I said, within each hospital, there are n users. It's the central DP. So when S equals 1 is sample size squared budget square. And when n is 1, you only have S hospitals, and that is local DP, so it's sample size budget square. So federated DP is something in between local and the central. Sorry, did I say? Yeah, federated DP is something between local and the central, and you can actually, it's an interpolation of these two different rates. And again, another thing I want to bring to your attention is this exponent. So the second and the fourth term, this is the non-parametric rate because you're estimating a function, so there's a non-parametric rate. And this is the standard non-parametric rate if you know about non-parametric statistical functional data analysis. And this rate comes with the private functional data rate. So in addition to the usual change in the effective sample size, we also see a different exponent here. Alpha, we assume the function is alpha Sobolev. So you can actually see this exponent here is larger than, sorry, this is smaller than that one here, which means it has a stronger curse of your roughness. Well, this is usually seen in the privacy literature. So the usual cost of privacy comes into two sources. One is the change in the effective sample size. You're adding noise, which means you are decreasing the effective sample size, and also it has a more severe curse of your model complexity. So yeah, that's the two things we can see. I have 2 minutes. I'm going to skip all this. I'm just going to talk about some open problems. There are lots of open problems, and every time I give a private talk, I can think of something new. So in addition to the things I'm writing here, probably I will just say something I'm very interested in at the moment. We've already seen the difference between local and the central, right? So the good thing about the local differential privacy is to give you a stronger protection of your privacy, but the problem is it has a more severe loss in the accuracy, and the central is just the other side of this story. So in practice, people do want to use a more central-like thing in order to learn your data better. What the central means is I give you a fixed sample size and do things, okay? However, if you are doing an online learning, so if you are doing a multi-unbounded problem or dynamic pricing or just some reinforcement learning or whatever thing, your sample size keep changing as your time goes on. So if you want to do a central version of this in the online setting, what is the best way to do that? Okay, this is a huge open problem now, and there are lots of different attempts. And usually people will call it joint differential privacy, but as far as I'm aware, there are at least 3 different types of joint differential privacy in that context. And none of this is probably perfect at the moment. So yeah, I'm happy to talk more, but I will just stop here. Thank you very much.
Thank you very much. So any questions from the audience?
I have a question. So, as far as I know, federated learning is usually applied for classification problems. So
It's for what problem?
classification.
Classification, okay.
Yeah, if it's classification problems, the generalization error bound will have a fixed rate. We can only compare the coefficient, because for classification problems, all the faster rate need a super martingale condition, like a Tsipakov margin condition, the Bernstein condition, and a central limit, some condition, and that cannot be hypothesis tested in practice. That's why usually we only have 1 over square root of n for the classification problems. If we are considering the DP and the federative classification, can you still theoretically analyze the trade-off between privacy and accuracy? Because the rate has the convergence rate is the same.
Okay, so I guess you are talking about generalization error here.
Yeah, because you are analyzing the min-max rate.
Yeah.
But as far as I know, min-max rate is usually only used for regression and some similar problems. For classification, the min-max.
There's also min-max rate.
No, the generalization error for classification is not a min-max rate, because we will not consider the worst the worst distribution. We consider a fixed data generating distribution.
Well, okay, so you can use the excess risk. If you use the excess, if your measurement is excess risk, and there's min-max rate, right?
No, it's not. Because for classification problems, we consider that the data come from the underlying P of x and y, and that P is fixed. It's not a capital P, a distribution family. But in regression problem, you consider the noise is Gaussian noise, but the true response function y equals fx plus epsilon. That fx can come from a very a much larger function class, you consider the Sobolev something. Then that's the difference, because in regression you only consider the the distribution of the noise, you will not consider the joint distribution.
Well, we can. I have my reservation to your thing, but I think that's basically one of the purpose of this workshop, which is to bring people from different communities. I think we are using probably slightly different terminology here, but yeah, we can definitely talk offline. Yeah.
Okay, okay, maybe. But I have another question.
Sure, please.
In DP, you consider that the two data sets only differ by one data point, and you cannot distinguish.
That's central DP, yeah.
Yeah, but my question is similar to machine learning. Sometimes if I want to unlearn 10% of data, they are not uniformly at random. It's like on CFR10, I want to unlearn a single class. The X will be related. So if you increase differ by some one data point or some data point to many, then maybe we can distinguish.
This is not for some, it's for any. It can be differ for anyone. It's not for some, it's for any.
Yeah, I mean, differ by any single data, right? But when there are so many data differ, but they are correlated. For example, they come from the same class, dog. And then you can definitely tell that dog is included in the training data or dog is not included in the training data.
Oh, wow, okay, so right, that's coming to the dependency issue. So the min-max rates I'm showing here, this is just for the independent data, and for the dependent data, yes, there's another story, yes.
Okay.
But it's the definition for the differential privacy is still valid.
Yeah, the definition is valid as long as you continuously randomly remove one data and then remove another data, it always holds. But if I remove 10% or 1% of the training data, but they are correlated, then it does not. The theoretical guarantee does not hold anymore.
Well, that definition, okay, yeah, we can carry on this later. I think it's coming to a bit of a subtle language issue. Yeah, we can definitely talk about that offline.
Okay.
Thank you.
Okay, thank you. Let's thank Professor Yi Yu again.
Okay, good morning again. So my role today is not to talk about new result to internal people, but I want to somehow give a high-level overview of our research to UK visitors, because the purpose is to open for collaborations. So it's nice to give some high-level overview of our research. So title is Recent Advances in Learning from Imperfect Information. So our target is basically reliability of machine learning systems. So it depends on training data, definitely. So one of the major topics for us is weakly supervised learning. So where training data contains kind of insufficient supervision, but still we want to guarantee that our trained classifier works well in some way. Then the second topic is label noise robust learning. So labels are usually given by human or some machinery. So labels are prone to observation error or human mistakes. This is unavoidable, but still we want to cope with it. Then the third topic is distribution shift. So we want to adapt it, because the world is changing over time, or because of some privacy constraint, we are not allowed to collect data as we want. Then our training data is kind of biased compared to the test distribution, and we want to overcome it. So that's a challenge here. Then the last topic is reinforcement learning. So reinforcement learning itself is a kind of weakly supervised learning, because we don't really have to directly give the supervision to the system, but still the system can somehow infer the best action. So only indirect feedback is given, but still we want to somehow design it nicely. So improving the reliability of machine learning system is always a big challenge, and it's a long-standing issue. So that's why we have been working on this topic for long years. Okay, good. Let me start from the first topic, weakly supervised learning. So already we know that supervised classification from big label data is extremely successful, or surpassing human already in speech, image, language. But still, there are many applications where big label data is not available. For example, at our RIKEN center, so some teams are working on like medical data analysis or natural disasters, robot control, brain signal analysis. So in these applications, collecting supervised information is quite challenging. So we want to utilize some weak supervision that can be collected easily. So naively, we want to say that, okay, we want to learn from small data, but learning from small data is not usually possible unless we have some strong domain knowledge. So instead of like limiting the number of samples, so we still require a large number of samples, but we can assume that so our data does not contain strong information. Some kind of weak information is only included, but we have many. But still, we want to guarantee that our trained classifier works well. So that's the challenge of weakly supervised learning. And today, I don't really go into the detail of how we solve the problem, but I just want to quickly report what kind of problems we can solve now. So one of the classic examples is positive unlabeled classification. So it is a binary classification problem where we want to classify samples into positives and negatives class. But for training, so we are only given positive samples and unlabeled samples. Unlabeled are either positive or negatives, but we don't know yet. And we don't observe any single negative points. So from blue and black points, so we want to separate blue and red. So that's the problem here. And we spent more than 10 years for this problem, and now we have good enough solution for this problem. Then the second problem, so unlabeled classification is actually quite interesting. So it is quite unsupervised. We don't have any single label, but instead we observe we are given two sets of unlabeled samples. And our assumption is that each unlabeled data set has different class pairs. Like for example, the top set, so this contains, let's say 70% positive points and 30% negative points. Then the bottom one, let's say 20% positives and 80% negatives or something like that. Then only from that information, so two sets of unlabeled data and class pairs, we can actually train a classifier and we can guarantee that it converges quite fast. So we potentially have a nice application, for example, in medical data analysis. So suppose there are two hospitals and each hospitals accumulate a large number of medical images, like CT scan images. But typically medical doctors are so busy, so none of them are annotated, all unlabeled. But suppose we have some prior knowledge. In hospital A, we have about 20% cancer patients. Then in hospital B, we have only 10% cancer patients or something like that. Then in principle, so two sets of unlabeled medical images and those priors, class priors, we should be able to train a classifier. And given a new medical image, we can identify whether cancer exists or not. So that's the kind of interesting application of this unlabeled classification. Then we also have a lot of multi-class extensions, like noisy labels, ambiguous labels, complementary labels. So they are all handled in a systematic way in the same framework, all based on empirical risk minimization. So we can basically apply this kind of technique to any loss function, any classifier, optimizer, and regularizer. So it's quite flexible formulation. And we published a book on this framework already 4 years ago. Then after that, so we made a lot of progresses even now. So we are having a mathematically unified framework for some class of weakly supervised learning problems. And we are still exploring new problem settings and new algorithms. And in addition, so we are doing some application research, like in speech denoising, reinforcement learning, imitation learning, and LLM fine-tuning. So those are very nice applications of weakly supervised learning. Okay, that was the first topic. Then the second issue is label noise robust learning. The formulation is quite simple. So now, okay, we consider supervised learning problem again, but output is noisy. So in the case of regression, one-dimensional regression, we have input X on the horizontal axis and output Y on the vertical axis. Then in principle, the blue points should lie on the red function, target function. But because the points are noisy, so they are Y bar, so it's distributed around the red line. But usually, we don't care, right? We are given Xi and Yi bar. And okay, just fit it. So we just use these squares. But this is a kind of classic problem. And do we still have to investigate it? For regression, maybe the problem was already solved. We don't have to care. As long as noise is additive and independent, then they are automatically canceled out, and we have consistency. So just big data helps. But in the case of classification, so labels are flipped, randomly flipped. Like this is a 3-class problems, and in principle, 3 classes are separated. But because of label flipping, so we have mixed labels like this. Then, so importantly, so we need actually a specific noise reduction mechanism to achieve consistency. Even for this simple problem, so we didn't still have a kind of solid answer. So it's actually a quite important message, because some applied people say, okay, we have big data, so okay, just apply standard machine learning technique, and that's fine. But in the case of classification, it's not always true. So we need a specific mechanism, noise reduction mechanism. And one direct approach to tackle this problem is to use noise transition matrix. So in the 3-class case, so it's a 3x3 matrix. And ij element basically means label I is flipped to label j with this probability. So it's clean to noisy flipping probability. And with this noise transition matrix T, so we can actually cancel the effect of label noise in a systematic way. So this was proposed by Patrini et al. In 2017. But to apply their method, so we need to estimate T in practice only from noisy labels. So that's actually the biggest challenge here, because mathematically, estimation of T from noisy labels is not solvable. So T is not identifiable. So that means we need some additional information to kind of limit the solution. Otherwise, we can't obtain a unique solution. So this was a kind of challenge for our team, and we spent many years to somehow tackle this problem, like utilizing human cognition property or some mathematical tricks. And in the end, so we had a kind of reasonable method to estimate it under mild conditions. So today I don't really go into the detail here, but we have a kind of, so here's a triangle. In the 3-class case, we have a triangle, and then the true noise transition matrix is regarded as expressed as an inner triangle. Then actually data points, noisy data points lie inside this triangle. Then so we just try to recover this triangle by shrinking the volume of the triangle. So that's the best algorithm we developed, and we can show that this converges nicely under mild conditions. So this is one of the, I think, best solutions for this problem setting, even though it was proposed already 5 years ago. But the real world noise is unfortunately even more challenging. So what we have discussed so far was so-called input independent noise. So T was only like class-wise. So this means that, so in the 3-class case, like we have similar noise over the entire domain. So that was the kind of assumption so far. But in reality, we have more noise near the boundary, and we have less noise if it's far from the boundary. So this is often the case in practice. So this means noise property is basically input dependent. So noise transition matrix T should be actually handled as a function of input X. So it is extremely challenging. And we try to provide a kind of realistic solution, practical solution in these papers, and they work reasonably well in experiments. But still, we need some heuristic or some additional information to solve the problem. So that's why we are now tackling this problem in a slightly different way. So I will cover this in the next section. Okay, then the third topic is distribution shift adaptation. And training and test data often follow different distributions, like due to changing environments over time. Like even like we are using LLMs every day, but if the US president says something, then yes answer was completely changed to no on the next day. This kind of sudden change happens in reality. So we want to somehow adapt our machine learning system to this changing environment. So that's a challenge here. Or even if the environment is stable, so still like we are not allowed to collect data as we want. Like suppose I want to train a classifier for a participant here today, but because of some privacy reason, I can collect data only from like left-hand side of the people. But I want to apply my classifier to everybody here. Then here is a clear distribution shift, and we want to overcome it. So that's a challenge here. So we want to train a test domain predictor using training data from different domains. And apparently, this is not a new topic. And already, actually, we organized the NIPS workshop 20 years ago at Whistler. And at that moment, there was no good name for this problem. And our workshop was titled NIPS Workshop on Learning When Test and Training Inputs Have Different Distributions. So this really clearly explains the problem as the title. And we had a lot of great speakers, and it was quite successful, actually. Then after a couple of years, we published a book from the workshop. And this is named and entitled Data Set Shift in Machine Learning. So this was the term we coined at that moment. But unfortunately, this term, data set shift, was not really used by any other people, and it was completely forgotten. But recently, so this topic was back, because now we have a lot of generative AI systems, and they need to survive or overcome this changing distribution. So the topic is back, but the name was different. So now it's called distribution shift, or in some workshops, it's called fine-tuning. So maybe the context is slightly different, but in any cases, so we need to overcome the changing distribution. So that's a challenge here. Then the classic setting is called covariate shift, where only input distribution changes. So here's an illustration of one-dimensional regression. Then the target function, this red one, doesn't change, but only input distribution changes. The training data come from the left-hand side, blue points, but the test data comes from the right-hand side, so these black crosses. And from blue points, we want to predict black crosses. So this is a covariate shift problem. And if we just naively apply linear least squares, we end up in having this green line. So it fits blue points quite well, but it doesn't predict black crosses well. Then, so this adaptation can be systematically done by importance weighting. So instead of just linear least squares, we apply this weighted linear least squares. The weight is given by PTE of x over PTR of x. So these are like a ratio of input densities between training and testing. Once we apply this weight, then we have a consistent solution. And for this simple illustrative problem, so from blue data points, we obtain this green line, and it predicts black crosses reasonably well. So that's the kind of application here. And again, this is quite classic. And already, like, we published a book on this topic more than 10 years ago, so 2012. And at that moment, this technique was kind of fancy, and we had a lot of industrial applications for this one. And it was used in many different problems, and it worked reasonably well. But then recently, so we are making a lot more progresses. Like, classically, we estimated this density ratio from data, and then estimated density ratio is used as an importance weight. It's a kind of two-step procedure. But now, actually, we can combine these two steps into like one single procedure, and joint importance predictor estimation is possible. And this works much better in practice, and also this has nice theoretical properties. Then we also consider so-called sequential distribution shifts. So we not only consider training and testing, but testing 1, testing 2, testing 3. So test distribution is also changing over time. And we want to apply basically online learning to overcome this changing distribution over time. Then nowadays, the most important topic is so-called joint distribution shift. So this covariate shift is like shift only in the input distribution. And the target function didn't change over time. But in this joint distribution setting, basically everything changes. P of x and y changes over time. So this is like a bit too challenging problem, because so P of xy changes means basically we can transfer data from completely irrelevant problem to another problem. It sounds like. But actually, formulating this joint distribution problem properly and tackling this problem is really important, because as a special case, this includes, for example, label noise problem, or it includes basically all type of distribution shift problems. And the biggest constraint in this distribution shift adaptation research is that we need to know the type of distribution shift in advance, either covariate shift or label shift or whatever shift. It's more like an assumption. But in reality, we don't know what kind of change happens in reality. So once we have a very generic method for joint distribution shift, then this is the first method we should apply in practice and see whether machine learning really helps to overcome this joint distribution shift. And now we have its extension to out of distribution, and we have more applications in language model alignment and test time adaptation. So these are quite important applications nowadays. Okay, then the last one is about reinforcement learning. So in reinforcement learning, an agent interacts with the environment, and agent takes an action, makes a transition, and then receives a reward. And it learns an optimal decision-making policy that maximizes some kind of aggregated rewards over time. And already it is quite successful in many applications, like in games, robots, language models, alignment. And here, so in reinforcement learning, so we need to prepare reward. So if the action is successful, we give a positive reward. And if the action is a failure, so we give a negative reward. And it is our job to design the reward function in reinforcement learning formulation. Or in practice, we need to learn it from data or some demonstrations. So this is, again, a long-standing challenge. And this is the most important piece to make reinforcement learning useful in practice. And we try to tackle this problem from many different aspects. Like designing good reward is always challenging. And so far, so we have a formulation of inverse reinforcement learning and imitation learning. So these are quite important. But they are more like supervised learning. Right? So we ask human to prepare demonstrations, positive samples, and try to learn the reward function from those samples. So that's the formulation of inverse reinforcement learning and imitation learning. But naively, we can somehow extend these approaches to weakly supervised learning or noisy labeled learning problem. So now we have a kind of weak version, noisy version of imitation learning, and that's more useful in practice. Or reward function can also change over time. Not only the environment, but the reward also changes. And naturally, distribution shift adaptation in reward modeling can be applied to many interesting problems, including language model alignment. Then finally, rewards are not necessarily given immediately. So one of the limitations of current reinforcement learning is that we need immediate reward at every time step. And we accumulate them and optimize it. But sometimes, depending on applications, we can't observe reward immediately at each time step. But for some interval, for example, for this interval, reward is 10, and for next interval, reward is 5. But we don't know the immediate reward at each time step. So here, so we try to distribute rewards, so by what we call reward back transformer. So we try to take the context into account and try to redistribute the summarized reward into each time steps. Then we can apply standard reinforcement learning technique to solve the problem. Then finally, so I want to cover the latest work by Yutin and Ivan. So it's about generalizing reward aggregation. In standard reinforcement learning, so we aggregate rewards by a discounted sum. So we have reward at each time step, and basically we take the sum over all immediate rewards. But depending on applications, other than sum is often useful. Like for example, in drug discovery, maximum reward in a certain interval is actually more important for evaluation. Or in finance, for example, portfolio optimization, so-called Sharpe ratio is quite important. This is a risk is considered here, and mean is normalized by the standard deviation. So this kind of risk-aware measure is actually quite important in critical applications of reinforcement learning. And indeed, if we consider a simple MDP, Markov decision process here, and then we consider different types of reward aggregations, then the best policy actually changes significantly. So either sum or mean or max mean, so best one changes significantly. So we want to handle various aggregation methods in a unified manner, so without really changing the formulation itself. So that's a challenge here. Then here, so we have a quite kind of elegant solution. So we consider recursion in reward aggregation. And the discounted sum can be naively expressed in a recursive way like this. So we have sum of like R1, R2, R3. So and gamma, maybe we can just ignore gamma at this moment. R1, R2, R3 summed. Then, so this is recursively expressed as R1 plus sum of R2, R3, R4. So it's recursion. And reinforcement learning basically utilizes this recursive form effectively. For example, the Bellman equation for state value function or state action value function or whatever. Then now, so we try to generalize this aggregation in a recursive form. So we consider basically 3 operations: initialization, update, and post-processing. And naively, so this discounted sum can be expressed in this framework. Initialization is just 0. Then update is just sum, adding a new one to the previous one. Then the post-processing is just the identity mapping like this. Then we can recover the original discounted sum. And this is more generalized. And following this generalized aggregation methods, we can basically extend the existing reinforcement learning technique to this version, only changing a few parts of the algorithm. And this contains a lot of interesting new aggregation methods, like discounted sum, discounted mean, discounted max, log sum x, range, mean, variance, top k. So these are, I think, useful in some specific applications, but we can handle them in a systematic way. Okay, so I quickly covered our previous research on weakly supervised learning, label noise robust learning, distribution shift adaptation, and reinforcement learning. Then what we are interested in now is this scenario. Now, a common foundation model is used by everybody. But these days, so these foundation models are kind of personalized to each user or specialized to each task and over various modalities. The situation is like this. So I'm here and I have my mobile phone and I download a common foundation model in my mobile phone. Then I have interaction with my AI system in some environment. But as we said, so environment is changing over time. So my interaction with my AI system should also reflect this changing environment, should address the changing environment. So to tackle this, we need to really investigate learning in dynamic environments more carefully. That contains online learning, continual learning, imperfect learning, data learning, or structured data learning, or sequential decision making, probabilistic inference. So these are kind of basis of learning in dynamic environments. Then another important issue is we have many users, many different tasks, and many modalities, maybe thousands or millions or even billions. So we need a kind of unified theory to dynamic and diverse environments. And to handle this, we may also consider topics like multi-agent learning or multi-agent interaction, or multimodal and multitask learning. And in addition, so this is a kind of society scale system. So we need to definitely care privacy issues or adversaries and also fairness kind of constraints. So we need to also consider this kind of social problems in this system. In addition, because the scale is so large, we should also take into account computational efficiency or energy efficiency. Of course, directly working on energy issue is not so possible for machine learning theory people, but still from an algorithmic viewpoint, we should be able to contribute to some extent, like large model learning, big data learning, distributed optimization, compressed data learning, and hopefully some new computing paradigms could be introduced in this framework. So this is just a high-level view of the current challenge. But initially, our standard machine learning topics are already included in some parts. But hopefully, they can be somehow extended to handle this kind of personalized and specialized system, so that we can have a unified theory in dynamic and diverse environments. So that's something I'm thinking is quite important for the future. And I think statistical safeguarding is really fits this framework quite well. So hopefully, like our collaboration can somehow fill some missing parts in this framework. Okay, thank you very much. That's all from me.
So I'm going to talk about, I'm pleased to have seen lots of interesting ideas. I think there's a lot of common ground, so I'm very excited to look forward to the discussions then tomorrow. So I'm going to talk about distribution shift in offline reinforcement learning. It's probably a different kind of distribution shift as was presented earlier on. And so what I'm going to do in this talk, in the first part, I want to kind of set up the scene, explain what offline reinforcement learning is in case you have not encountered it before, and kind of explain the source of these problems, the distribution shift, and then give you a very high-level overview of some of the methods that we have developed to deal with these issues. So I'm sorry to repeat again the usual reinforcement learning loop, but I think it's a good place to start. So we're interested in sequential decision making, right? So we want to train an agent, a computational agent, to make decisions autonomously, and this agent, the decision maker, interacts with an environment, which is effectively the problem. So the environment can be measured or observed. So the agent will observe a state S that comes from some distribution, which usually we don't know. And then based on that state of the environment, the agent will draw an action from a probability distribution, which is the policy that we want to learn, which is conditional on that state. It will execute this action, and then the environment will give a scalar reward, which is the learning signal for the agent. And effectively, by trial and error, the agent wants to learn this policy, and the game here is not just to maximize the next reward, but to maximize the expected return, so the expected sum of future rewards, which sometimes we discount because we prefer big rewards sooner rather than later. And so this is an interesting problem, right? Because the data set depends on the policy that you are learning. So you learn the policy changes, and the data changes accordingly. And it's a very well-established framework. The point that I'm going to make is that in the real world, this is very difficult to do, right? So if you think about, you want to train a clinician AI, an AI that makes decisions to treat patients. You can't do this, right? Because you can't deploy a policy that is suboptimal on real patients. Or if you're trying to learn a financial trading strategy, you can deploy a policy that makes bad investments, you end up losing all your money, right? So you can't really learn in the real world by interacting with the real environments. Of course, you can simulate some environments, and this is very established if we look at games or robotics, where you can simulate the physics. But in many other kind of real-world examples, this is quite difficult to do. And so what can we do if we can't really interact with the environment? Well, then we have no way of interacting. So what we can do is try and find an historical data set, so some data that we have collected, which is in the form, typical kind of form that you would expect, where you have a state, an action, an next state, and a reward. And today, with the digitalization being kind of commonplace, you can find this sort of data pretty much everywhere. If you look at hospitals, they have now 20 years of historical data. Financial systems, you have many years of trading data and so on. Now, the catch is that in the online setting, the agent was able to learn by interacting, so was able to see the effect of an action by receiving the reward. In this case, the agent must learn through some counterfactual reasoning. So it cannot really execute an action that is not in the data set, right? So he has to think, what could happen if I executed this action? So this is a much harder problem to deal with because we don't have the two components of reinforcement learning, which is exploration and exploitation. We could just exploit what we've got, but we can't really explore. And the objective is still the same, right? We still want to maximize the returns. Right, so distribution shift in this setup is a major issue. So in this cartoon, I illustrate the state action space. So x-axis is state, y-axis is the action. And so these colored regions represent some sort of occupancy measure of probability distribution over state action pairs. So the green one is the one that is generated by the behavioral policy. So the behavioral policy is the policy that generated the historical data. So at some point, somebody generated the data, and we call that the behavioral policy. In reality, it's never a single policy. So if you think about getting data from hospitals, there will be many doctors acting differently. Some are much better than others. There will be many different hospitals. So in reality, what we call a behavioral policy is really a mixture of different policies. But nevertheless, I will refer to it as a behavioral policy. So this is the support of the data that we've got according to the behavioral policy. And this is where the policy that we are learning wants to go. So it wants to go potentially away from that data. But we have no data here, right? So when the policy, the target policy that we are learning wants to query a value function in this orange area, it just has to rely on extrapolation. So there is no way they can reliably estimate the Q values in that area because we have no data. So this is creating some issue, right? But let me be even more precise about the nature of this kind of distribution shift. So now let's look at one state. So we're focusing on one state, and these are all the possible action at one state. And suppose that this dashed line is the true Q value function, right? It will tell you how good it is to be in that state if you take any of those actions, and then from that point on, you continue to act according to the target policy. Well, we have some data here. These red dots are the points that we have collected in our data set. So there are some regions where your estimated Q values, which is the continuous line, will make a small approximation error. But there are some areas where you have some deserts where you have very little or no data. And in those cases, in those regions, you will have a very large approximation error. But now, what we do when we learn policies is that we act greedily with respect to the Q value. So we take an action that will maximize the Q values. So if we are in regions, let's say like this, where you have a very large approximation error, you're still taking the action that maximizes the Q value. So you're actually maximizing your error, right? So we are introducing, by sort of definition, because this is the target of the Bellman equation, we are introducing large error due to the approximation errors. And as you know, through the Bellman equation, this error will then inflate the Q values of other states, right? So this is a really severe problem because we're not only making an error at this state, but we are propagating the error all the way through the state space. So what we want to do is try not to make this kind of errors. We want to limit this sort of extrapolation errors. Okay, so you will say, well, why can't we just do behavioral cloning? We've got some data, and we want to replicate the action taken in the data set. So you could just set up a simple supervised learning problem where the optimal action is the action that minimizes some sort of error between your predicted action and the observed action, right? And this kind of makes sense only if your data set is a data set of expert data. So if you ask a bunch of experts to give you a data set where you have demonstrations of how to really solve the problem optimally, then you want to imitate the data set, right? But this never happens, right? In practice, your data sets are suboptimal. As I was saying, you have a mixture of different policies. So what you really want to do is to imitate the subset of data that comes from the good experts or the good demonstrations and discard the bad ones. So if you have this sort of mixed quality data set, you have some sources of error. So for instance, let's say you are at a state S, and one expert say will go up, the other one say will go down, and then you take the average action, you end up in a state that doesn't really make sense. Or if you make a small error, so you start at the state S, take an action, we will take you a state which is slightly different from the expert state, and then you continue to drift away from the expert kind of trajectory. Very soon, you will end up in some parts of the state space that is very far from the distribution of the data, right? So this error kind of compounds. So behavioral cloning is not really the way to go. What we want to do is take a data set of suboptimal demonstrations, suboptimal data, and try to learn a policy which is better than the better policy that was in the data. Seems crazy, but that's kind of the definition of what we're really trying to do. Now, there are three kind of families, if you like, of methods that try to achieve this. And of course, there are ways to mix and match and different way to implement each one of these ideas. But these are kind of the three major directions, if you like. So one thing you can do is to do behavior regularization. So you estimate your policy by maximizing the expected Q values as usual, but you are trying to push your target policy, the policy pi, as close as possible to the behavioral policy mu. So this is mu is the policy that generated the data. So you're saying, well, I can let my policy pi to learn, and you can go away a little bit, but not too much, and you penalize some sort of distance between these two probability distributions. In this case, it's the chi-L divergence, but it could have been something else. And of course, you have a parameter that will control how much you penalize. So something else that you could do is you can learn your Q value from the data as usual, but then trying to penalize the Q value. As I told you a few minutes ago, some of these Q values will be overly optimistic. They will be inflated because we take the max. So they will be very high. They will tell you, yeah, this is a great state and action pair, when in reality, this is just due to the epistemic uncertainty and the fact that we have little data in the area. So we push down the Q values when we think that we are in an out-of-state region, right? So there are different ways to detect it. This is one, but the idea is the same. So if you can detect out-of-state or out-of-distribution state action pairs, you can push down the Q values. And then one third kind of direction is to say, well, let's not allow the policy that we are learning to go away from the domain of the data. So let's estimate everything, the Q values and the policy, using only the data sets that we have in our data set, the data point that we have in our data set. So this example is using expected regression to kind of mimic the max Q values, and then we can extract the policy from those Q values. So these are kind of three different directions. If you look at the literature, you will see that pretty much every methodology is using some elements of this, and as well as the methods that I'm going to discuss in a minute. So what I want to do is really give you a high-level overview of some of the methods that we have developed for three set of problems of increasing complexity. So we will start with the very basic single agent offline RL, the same setup that I've just discussed. And then we'll make it a bit more difficult, right? So we will go onto goal conditional reinforcement learning, where you don't have rewards at every single time step. You just have a reward, a goal that you want to achieve, and then you're only rewarded if you achieve that goal. Otherwise, you have zero rewards, which makes it very difficult. And then finally, an even more challenging situation is the multi-agent reinforcement learning, where you have a bunch of different agents that need to learn how to coordinate their action and solve a task that requires some sort of collaboration, but they need to do it again only with historical data. Okay, so let's look at this first problem. So one of the first things we did when we looked at this kind of class of problems, 2 or 3 years ago, was, well, behavioral cloning is bad if you don't have expert data. So what can we do? Can we take the data, which is bad, and try to make it better in a way that makes sense probabilistically, and then do behavioral cloning? So the idea is the following. Suppose you have different trajectories in your data, and this is worse than this is worse than this. So this is a state, this is an action takes another state, and so on and so forth. So you can write down the probability of any of these trajectories in this way. You have the probability of the first state, and then you multiply the probability of reaching the next state given the previous one, and then you multiply by the probability of taking an action that actually took you from here to there, conditional on those two states. It's a very awkward way of decomposing the probability. It's perfectly fine, but it's not really, it's not commonly used, but we use it because if you think about it, what this is telling you is that, well, first let me pick the st+1, the next state, carefully, so that is according to this probability distribution, and then I figure out which action I need to take to actually guarantee that this is plausible. And so what we can do, if we do this, in a second I will tell you how to do it, we can introduce these stitches. So we can jump from one trajectory to another trajectory. So we replace this next state by this next state, which is another trajectory, assuming that the probability of moving from here to there is plausible according to some dynamic model, then of course we need to estimate from the data, and then that the value of this trajectory goes up, right? So it's a perfectly good way of stitching two trajectories together because the value, the future value of the new trajectory is higher than the previous one. And so I'll probably skip some of the details, but effectively we set up some mechanism by which we decide when the probability is big enough to jump and when the value is large enough that is worth actually jumping. And what we do is that we follow the trajectory, we introduce these jumps, we have a new trajectory, we estimate some value function, and then we do behavioral cloning. And then you can keep doing it, right? You have improved the quality of the data once, then you can do it again, and then this will converge. And this is guaranteed to give you a better policy than behavioral cloning, just by definition. And we did a lot of different tests, and it was very competitive with some state-of-the-art, 2 or 3 years ago when we did it, kind of algorithms on this D4RL data set. So this is a data set that has a bunch of different tasks using some robotic simulators. So you have a locomotion task, navigation task, manipulation task, and so on. Right? So now, this is not extremely elegant. We are just kind of messing around with the data, improving the quality of the data. We estimate some value function, but we're not really doing reinforcement learning end-to-end. So we then try to improve upon this and came up with another idea. And so one of the most kind of famous algorithms, at least back then, was the batch constrained Q-learning, which is basically saying, well, you can estimate your policy by maximizing the Q values, but this maximization should only happen with data points in the data. With state action points in the data. So this is an example. Suppose you have a maze, and each one of these trajectories is a data point, right? It's a trajectory that we have in the data that we can learn a policy from. And let's say this is a starting point, this is the end point. Ideally, you would need to be able to reach the end point with an optimal policy. So what the batch constraint algorithm can do is that it can stitch together trajectory only if the action that connects two states has been observed in the data. But if there is no action in the data that connects two states, then that action is invisible, and then you will miss. So you will miss some really interesting stitching opportunities just because you have not taken the particular action in your historical data. And this is what we wanted to enable, right? We wanted to enable this jumping from one trajectory to another one so that you can basically find your way to the goal in this case. So how do we do it? So we replace the QSA function, the Q value function, with something called the QSS prime, which is now giving you the expected value of jumping to an X state S prime, given that you are in S. And we use kind of similar ideas to what I introduced before, right? We try to identify these valuable S prime states that are in the data set by stating some kind of conditions that we want to be satisfied. So this function F will give you a predicted S prime, and the S prime should be in your data. And this is an inverse model that, given the state and the next state, S prime will give you the optimal action that you need to take in order to move from S to S prime. And so if you kind of set this up, you can do end-to-end learning of the Q values as well as the policy. And the way this works is that you will learn these best next states which are in the data by only maximizing now with respect to this set, RS, which is the set of reachable states. So now we don't have just all the states that are connected, that are connected with R, but that could be connected to S, but they could be connected to S through these models. So it's a model-based kind of approach. And we can prove some properties. We can prove that the algorithm will actually converge, and the conditions for convergence are actually milder than the traditional Q-learning conditions, where you need to visit each state and action pair infinitely often. Here we're just assuming that you can visit each state infinitely often. Okay, so this was kind of a nice way, which we, by the way, called state constraint offline RL. Now, another way of approaching this problem is to, as I mentioned before, to have a pessimistic estimation of Q values. So try to be pessimistic. So what I mean by pessimistic is that ideally, if you had the posterior distribution of the Q value given the data, so if you have access to the entire distribution, you will take the minimum. So you will stay very close to one tail of this distribution. Now, unfortunately, we cannot easily estimate the entire distribution unless we do some Bayesian reinforcement learning, which will introduce other challenges. So one easy way to do it is to build an ensemble of Q values. So we use different random seeds, and for each one of these seeds, we learn a Q value function for the same state and action, and we see how much variability there is. And then we can take the minimum of this ensemble, and it's a very good kind of approximation of the true minimum. And so there were some papers showing that if you train some algorithms like soft arithmetic, SAC, by using this idea, you can achieve really good performance. The catch is that you need to take a very large ensemble size. So you need to build an ensemble of maybe 500 of these Q values in order to reliably estimate the minimum. Right? So this is computationally very demanding. So our kind of starting question was, can we achieve something like this, where we use, we quantify the uncertainty, and we use the uncertainty to push some, introduce some pessimism, but do it in a computationally efficient way. And so the idea that we proposed was to combine these two different families of methods. On one hand, you have this pessimistic estimation of the Q values. And on the other hand, we're also trying to push the target policy close to the behavioral policy through some sort of distance of between the two. This is a very, very simple one, but this is kind of a more general idea. So what happens is that by pushing these two distributions to be together, we are already reducing the number of ensamples that we need to reliably estimate the minimum. And so by carefully tuning beta, we only need a very small number of Q values in this ensample to achieve the same performance as the previous method that doesn't use this regularization. And so again, this is 2024, so a couple of years ago. It was still really good performance, but at a fraction of the computational time. Okay, I'm not sure. Yes.
Beta, hyperparameter.
Yeah.
In practice, how do you set beta?
Oh, well, you try. So this is like the elephant.
If you try, still you can't evaluate it.
Yes.
Right.
So this is the elephant in the room of offline reinforcement learning, right? Where you don't know what you don't know, and the only way to know is to actually run the policy, and then you find, you have a grid of value, and then you find the right beta. And so this is common to every method, right? Every method will have some hyperparameters, and everybody will then ask the same question, but how do you tune your hyperparameters? So still the day has to come where there is kind of a magic tool to estimate the hyperparameters without relying on the environment. So I guess where the field is a very recent field, just maybe 2 or 3 or 4 years. I guess what we're trying to prove is that it is possible to do it, and then you do some sensitivity study and you check how sensitive your algorithm to beta. And in this case, yes, there are some values that you want to avoid, but there is a range that pretty much work nicely across different environments. And then you say, well, take that beta in that range. But it's a great question. So another challenging task is goal conditional reinforcement learning, right? So now we started a state and we want to achieve a goal, and we get absolutely no rewards all the way until we achieve the word. So we have no way of knowing if we are going in the right direction or not until we achieve the final goal. But this is, for instance, in robotics, what happens naturally, right? You want to grab an object. If you grab the object, you get a reward, a positive reward, otherwise you get a 0 reward. And in the offline RL setting, this is even harder because you have only a subset of these goals, and you need to generalize and learn a policy that will work for any goal out of distribution, right? And so this is quite challenging. So how to generalize across different goals with very limited training data is really the challenge. And then maybe just give you one quick example how we did this. So I told you that this behavioral policy is in fact a multimodal distribution, right? Because there is data coming from multiple sources. And if you ignore the multimodality, you just average across different modes, you end up with some rubbish, right? Rubbish actions. So what we do is we embrace the fact that we have different modes. So we use a mixture of Gaussian distributions to model these different modes. And then what we set up is an algorithm that rather than trying to evaluate the Q value of a state and an action, will evaluate the Q value of a distribution. So what we called an hyper Q value. So it will evaluate how good it is to pick any of this distribution, and it will then, that's why it's called learning from one mode, because we pick the best mode that we can, we learn from one mode, and then we do imitation learning with actions sampled from that mode. And this works really well. And there's also some kind of theoretical guarantees. I just want to kind of explain the challenge of multi-agent reinforcement learning, because it's quite challenging. And actually, this is a very new problem in this area. So now you don't have one agent, but you have multiple agents. So now you have a centralized Q value where you evaluate the quality of this action, of these states, when all these agents take their actions jointly. But then the policy is decentralized. So each agent will learn its own policy, and they all can act kind of independently once they've learned the policy. The problem is that this is a combinatorial problem, right? So you have an exponential number of actions, and for any given configuration, it's very likely that you have no data point that contains exactly the configuration, any of these configurations. Maybe some of these actions will be seen in your data, but not exactly the same kind of tuple. So the data, in other words, is even sparser than the single agent case, right? So you have very few examples. And so this makes it really difficult, because when you need to update the target for your Bellman equation, there is almost always, this tuple of actions is almost always out of distribution. It's never really seen in the data. So what people did was to update all these actions jointly. But again, if you update all these actions jointly, the probability of that tuple being out of distribution is very high. But this was just an easy way to approach the problem. Or you could just update one action at a time, which means that you assume that the actions are conditionally independent given the state, but that's a very strong assumption, because these agents are multi-agents, they need to coordinate, so assuming that they are conditionally independent is a bit too strong. And so really the problem was, how can we estimate the right number of action to be updated at each state? So this is a state-dependent problem. For each state, there is an optimal number of actions that need to be updated simultaneously. And so we proposed this algorithm called adaptive partial action replacement, basically try to build this target using a mixture of different Q values, and we try all the possible value from 1 to n. So we try to replace one action or two actions, 3 actions, and we weight this Q value contribution by a factor that depends on the epistemic uncertainty of the Q values. In other words, if the Q values are very, there is a large kind of ensemble disagreement, that means that this is large, the weight is small, and so that particular Q value gets a small weight. And the idea is that if you have sort of random data, it's better to update them independently almost, because you don't break any correlation pattern. If you have expert data, it means that the agent have learned how to coordinate, so you need to look at the entire block, and so you would rather prefer to replace all the actions in one block. And so this very simple algorithm can perform really well in some multi-agent problems. Okay, so we've done a lot of work in this area. I mean, I think, as I say, this is kind of a new emerging area, so there is a lot of work to be done, and there's a lot of future direction. I'm not going to go through all of them, but as I say, I look forward to our discussions today and tomorrow about this. Thank you.
Thank you. Thank you for your presentation.
Oh, yeah.
Any questions?
Hi, thank you for the talk. I have a question for the multi-agent RL. So just like one of the last slides where you had like the, I think the variance, one more, one in, to the back.
This one?
One to the end, sorry. Go forward, please. Yeah, so here the weighting is 1 over standard deviation, or the WK. So the UK is some notion of uncertainty or variability of
So
how
yeah,
the...
so this is the So you have the different Q values. You have an ensemble of Q values. And so this is a measure of how much they disagree. So if they disagree a lot, it means that we are in a high uncertainty.
I mean, is disagreement always bad? I mean, could it not be that some agents specialize for certain aspects, so then you have like a coordination?
So this is disagreement in the Q value, in the estimated Q values. So it just depends on epistemic uncertainty, right? So if you think of this space of all the possible tuples of actions, if you are in a space with low density action, the support of the data is very sparse, there will be a lot of disagreement there because the Q values cannot agree what the actual value is just because there is little data. So if they disagree a lot, that means that we need to update smaller components at the time. If they all agree, it means that there is a lot of data. That means that the agents have taken actions jointly in that part of the space, and so we try to update the actions simultaneously. That's kind of the intuition. But yeah, so it's not disagreement in the action, it's disagreement in the Q values.
Thank you for the great talk. I have a question. So basically you introduced many methods that use a Q function. How about if some algorithm for post-training of a foundation model, like a PPO use V function, or DPO use policy gradient without either Q or V?
Yes. I mean, so for this kind of problem, I mean, most of these are tested on sort of robotics manipulation and sort of that. So this is the standard way. I mean, sort of soft, so actor-critic sort of methods where you have a critic, Q value or a V function, and then you will get but if you're looking at applications of these things in, let's say, LLMs, reinforcement learning for human demonstrations or different kind, then obviously you can play around, but there isn't too much yet in this area for those.
I feel that the distribution shift of DPO data is really a serious problem.
Yeah.
Like it's offline, but it's collected a long time ago, but now maybe it's changing.
Yeah, absolutely. So, I mean, most of these are off policy, and but yeah, of course, I mean, if you do PPO and on policy, it's a different kind of setup. Yeah.
Yeah. Thank you. If there is
Thank
no
you.
more questions, thank the speaker again.
Okay, thank you very much. My name is Dai Minowa from JST, Japan Science and Technology Agency. Thank you very much for giving me 5 minutes just to introduce our ASPIRE program. And first, ASPIRE program scheme, and now, second is now its new call is open. So it's a good advertisement chance for me. Thank you very much. First, ASPIRE. ASPIRE, how it works. ASPIRE is a framework that accelerates and expands research through international circulation of talent while fostering early career researchers. It also aims to encourage well-funded research teams to further promote collaboration. So JST fund for Japan team and top researchers and the counterpart researcher joint research. And also they promote mobility on the lab, the early career researchers dispatched to other countries. This is a feature of ASPIRE program. ASPIRE places emphasis not only on research, but also an emphasis on talent mobility and networking. This time, talent mobility aims to supervise early career researchers as future leaders through talent mobility activities. For example, travel expenses, including accommodation costs, and research expenses in partner countries can be covered. And also networking aims to build a network between top researchers in Japan and science, technology, innovation, advanced countries and regions like UK. And there are 2 types of ASPIRE. One is call for Japan-based researchers. 2 is joint call. JST is supporting through joint call to Professor Ishida, and also Professor Wenkai was supported by UKRI. This is the ASPIRE joint call. Today, I'd explain about the call for Japan-based researchers. This is JST support Japan-side researchers, and also Japan-side researchers dispatch young researchers to other countries, and also UK to Japan also be covered about under this call for Japan-based researchers. There's a Japan call for researchers. There are two categories. One is for top scientists, and the other is for rising scientists. And there are 7 research fields, including AI information and intelligent robotics, and biotechnology, energy, materials. So, and the partner countries are selected by the government. There are 21 countries and regions. And also for top scientists, there are 500 million Japanese yen for 5 years. And for rising scientists is 90 million Japanese for 3 years. And so there are 7 research fields. One is AI information and intelligent robotics. This is a detail about the theme of this AI theme. This is a comprehensive studies in informatics, including artificial intelligence, fundamental information science, computational infrastructure, and human information science, together with various applied materials domains. And adding to this, from this year, the intelligent robotics was added. And so our theme is very broad, so we welcome top researchers from broader research theme. And there is 2 requirements on ASPIRE program. One is outgoing and invited researchers. Early career researchers must travel to partner countries and conduct research activities there for about 1 year. Researchers from partner countries must be invited to Japan side team for a short travel. Number 2 is restriction to use of budgets. At least 70% of the total direct expenses must be allocated to fostering early career researchers. This includes building and expanding international networks for advanced research and development, promoting research mobility between Japan and the UK and countries. This providing opportunities for top-level international research collaboration. And as Professor Miyano explained, that ASPIRE was built 3 years ago, and there are so many cores are now supporting. In the Japan side core, there are 113 projects was supported, and joint core 17 projects. So ASPIRE UK joint core AI now JST supports Professor Ishida on this category. And this is the final page. This is advertisement. ASPIRE 2023 core is now open. So deadline is May 19. So we welcome applicants for Japan side researchers. Thank you very much for explanation.